So the next talk is by Tieyong Zeng from Hong Kong Baptist University, and it's about two-stage, three-stage methods for image segmentation.
So great thanks to the organizer for inviting me. So it is my greatest pleasure to present some recent work on image segmentation. So just now, Professor Prof introduced a very nice background related to image segmentations, and so this will be much easier for me.
I'm sorry, I can hardly hear you from here.
Oh, sorry. Works? No? Okay. So this is collaboration work with many people, including Professor Raymond Chen in Chinese University of Hong Kong, and also Mina in Kaohsiung. So the target of the image segmentation is very simple. We try to use one simple method to segment different image. For example, this kind of image you have many image texture, and this one you have is heavily noisy, and this one you have some broken part, and this kind and we try to segment the image in a uniform way, 3-phase, 4-phase, or more phase. Okay, so. So the idea is very simple. We start from the classical MS model, and then we provide a two-stage model, okay, which is strongly related to this previous model. Okay. So our model is strongly related to the MS model. Then we extend our work to general case. For color image, also for medical image. So this MS model is just minimize is energy minimization problem. Okay, so here, so F is your target image. Then you decompose your image into a smooth part G, and you have some contour gamma here. Okay, so this model is well known that very difficult to handle. Okay, so it's strongly non-convex. Non-convex. So the MS model has 3 parts. So this data fitted term, and the homogeneity of the G, and also the contour. Okay. So here, okay, the length of gamma is just the H1 Hausdorff measure of the length. So it's heavily non-convex. So a simplified MS model we can say is the convex model. Okay, you take mutants out, then for 2 parts you have to be constant. So you have C1, C2. Okay, so the classical level set method can be applied. So it's highly cited. Okay, but it's still rather complex, and it's still non-convex, and it's very difficult to handle multi-phase cases. So for us, okay, we want to consider a simple model. Okay, simple model. So what do? We propose a two-stage segmented approach. So in the first stage, we will solve H1 minimization model. Okay, H1 minimization model, and in the second stage, okay, the data can be clustered, okay, into phases. Okay, so the idea is here. So from the origin this model, okay, you have 3 turns, right? 3 turns. So the first turn, okay, is easy to handle, and the second turn we replace this one with some release lemma. Basically, it says that when the measure of gamma is 0, then this one the nearly the same. And another theorem tells you that the length of gamma is somewhat, okay, related, but not exactly the same, but it's related to the total variation of this G. Okay, then you minimize this model. So when you minimize this model, you get a G. Okay, then you do some clustering on the G. You can get the boundary. Okay. So this is very simple. Okay, basically tells you that okay, the measure is 0, then this one is 0, so you can do it. So the second part is that we prove a related theorem, okay, similar to Milani-Kolova's work. So we can prove that, okay, suppose this is the sigma inside gamma, you can do that. You have G1, G2 as two parts, then basically when you minimize M's model, you can decompose this into this long terms. Then okay, what you can do that this one is related to some u, okay, some u, okay, minimize the total variation of this one. So this is a result, okay, parallelism with this previous work here. So anyway, the basic idea is that okay, when we do some, we want to understand the length of this gamma, then is related to, okay, related to the version to u, and because in certain case, okay, the phase of this g, usually after you get a u, the phase of g you can be obtained from the series holding, okay, series holding. And one key observation is that, okay, so basically when you, the length of this kind of gamma is just the measure, okay, of the jump set of the g, and roughly the same in many cases is related to the jump set of the g. Then that's to say the gradient, okay, the gradient of g in fact you can use this one to approximate the gradient of u, okay, when you do it. So now, okay, we can provide a convex, okay, model, okay, convex model. So basically, what we do is in the stage 1, okay, stage 1 you have g, okay, L2 turn, and this is from the previous model, and this you have the L1 turn. Okay, you put it together, you get H1 model. Okay, this model has already been used by Professor Hinton-Miller for image restoration for image. So this is stage 1. Okay, after you get this image G, okay, you still need to get contour, right? Then you can do some. Then this one is you can extend it to the general case, de Broglie, or many cases. And after that, okay, so after that. Later, what you will do is that after you get a G, okay, you do some series holding, okay, do some series holding. So this is stage 1, okay, very simple, because now our model is a classical H1 model. Okay, we have very nice properties for this kind of things, right? We can prove the unique minimizer and mild condition, and sure, because this is a very simple model, you can have many good optimization approach to minimize this model. Okay, so then the stage 2. Okay, after you get this kind of G, okay, what you do is just you do some threshold this G, then you can get some piecewise constant images. Okay, so let me summarize the two-stage approach. So we first minimize the H1 model here. Okay, you can use the ADM method or other method to do it. Okay, so and then as the second stage, if you want to get the segmentation image, then you need to determine some thresholds, okay, from the G. So what very simple method, you can use the k-means or other method. Okay, once you define this these parameters, then you can get your k segments. Okay, you get k segments. So the numerical aspect of this stage 2 is also simple. Okay, so when you have this kind of G, okay, we can use k-means or other method. Okay, you can obtain this values. Okay, values, and then you just do your holding. Okay, and then this is very fast. Okay, as the number of the phase k and the parameters rule can be determined after G is fixed. Okay, after G is fixed. That's to say, there is very little commutation when you change this G. Okay, and rule. Okay, so. Let me show you the solution image. As you say, you given this kind of image after smoothing, okay, of the H1 norm, you get a smooth image. Okay, get a smooth image. So this, and when you see this smooth image, you can see that the texture here is heavy, right? But then after smoothing, okay, you get something like that. Then for this kind of image, okay, it's rather flat, and it's very easy to do segment. Okay. So let me show you the result. So this is the given image. So this is the Chavez model. Okay, and so we can tune the parameters. Okay, change the parameters. And this is our prism method. You can see that when we change the parameters, the result are somewhat reasonable because the texture was removed. Was removed. So you can use different parameters. For example, this is determined automatically by k-means, but you can slightly modify to get a different result according to you need. You need. And for other image, for this kind of image, you can see that this one is broken. It's broken. So we can get our solution image. Get a solution image. Then you can hold it by different parameters. So you use one parameter. This is broken, but you can slightly change it. Then you can connect it. So because this is triplet image, somewhat this one should be connected because it is a blood system, and so you compare a little bit with other method, you can see that roughly slightly better, slightly better. And this is three-phase segmentation image, So given the image is here, so our solution image is a smoothing part, smoothing part, and then you use k-means overlay. You can automatically determine the parameters, and then you segment it into three phases. You can see that for some other method, for example, this one is very nice, but then because this one is used constant image to approximate this one, so here it is broken. But for us, it is somewhat better. Somewhat better. And if you check carefully, sometimes for some points, this kind of points have some problem, but for us, it's okay because we do some smoothing, we can eliminate some the tiny structures, tiny structures. So this is for four-phase image segmentation, four-phase. So you have some given noisy image, use a piece constant method, then maybe you have some problem. But for our case, you can see that clearly we can separate these four phases. Four phases. And then our model, because it's basically is an image restoration model. You can integrate the blurring there. So if you have for the observation image, if you have some blurring, but still. This one we can still recover the faces. And the convergence of the algorithm is clear because it's a very simple model, right? You use some classical method. You can see that our method is very stable. It's very stable, and you can consider the comparison with CPU times because our model is convex, right? It's a very simple model. Then roughly, in fact, this kind of model, so it's very fast, it's very fast, just seconds you can get the result. So now, we can also extend this kind of model, to other cases. For example, we can extend this model to the non-Gaussian noise model, So, for example, the Poisson or multiplicative gamma noise. So basically, is the image if satisfies this one, then or the gamma noise, and you use some logic, some logic there. So what you need to select change is just the altitude turn you change to some turns adaptive to your noise, So we use G minus F log G turn, megaton, and then it's also very simple, right? So you can quickly minimize it. You have some better mathematical properties for this kind. And in the second stage, the same. You can show the solution to get the phases. So let me show you more result. So this is original image. You have some noisy and blurring result, and also here is our result. Result. And it's very interesting to notice that you have some tick here, and then we also have some kind of tick here. So you see. And also we can apply this one for gamma noise. The original image is here, and you have some gamma noise here. So these are the this work is piecewise constant work, okay, of Professor Tai. So it's pretty good, okay, it's pretty good. But the only problem is that you have to give this method a very precise parameter, okay. You should define the level of this kind of things. Otherwise, you could get a different result, okay. And for our method, okay, you can still automatically get the parameters. You can get this solution, okay, get this solution. And we can also test the image with some vary intensities. Basically, tells you that the intensity moves slowly here, okay. So and use the previous method, for example, here is not so good because you try to use just one constant to approximate, okay, but it is slightly changing, okay. It's not due to the noise, so maybe the result is not so good. And this is our method. You can see that we can clearly determine the boundaries. Okay? And then, okay, another extension we want to do the color image segmentation. Okay, so we can slightly modify it. Okay, so because basically originally is H1 model. Okay, H1 model basically is you want to smooth the image, right? But then you have two parameters, right? So if you want to eliminate one parameter, so we try to do is use this kind term. Okay, basically this one. If this one is epsilon, this is classical approach to minimize the TV, right? But and it's noticed that there you have some smoothing. Okay, but the smooth here is what we need. So we just use this model. Okay, this model. So this and we can, because we want to handle the color image, we can use the vector toleration, okay, vector toleration, and then it's related to minimum surface, okay, surface. So, but basically you have some extra term here, but we don't want to handle this one. We want a simple model. So anyway, so what we do is minimize this this kind of minimization. Okay, this is the data fitted term. Okay. So okay, so our model, okay, is minimize this kind of turn. Okay, so so basically it's a vector TV turn. Okay, vector TV turn. And for this discreting settings, you can still use prime dual method to handle this one. Okay, you can use method any method you want. Okay, it's a very simple logic. And let me show you one result. So this is the original image, and then this is image what you observe. Okay, from this one we can get some smoothing image. Okay, it looks smoothing, but when you determine one parameter, then you can find the contour there. You can find the contour there. Okay, so the second stage, okay, we can also slightly modify it. Okay, use the hair climbing or other method. Okay, to handle this one. Let me show you some numerical experiments. Okay, we compare with some previous method. One, this is the BCMS model, or is the pulse model. Okay, pulse model. So this is the given image, and we want to do two segments. Find the two segments. So the previous FRC does not work so well. PCMS looks good, okay, because basically you use the constant to approximate it, okay, and DPP is rather you have something here, okay, not so good. And then for our method, you can see that we can nicely segment this kind of things, okay. This is for this image you have to give the constant, give it the parameters to this one, okay. We have more image, okay, more image, and basically. So this kind of method now is not so good because you have some bright changing here, so sometimes it's not so good. Okay, but then for our method, you can see that we can determine the 4 segments. Okay, 4 segments, and more image. Okay, more image. So you have the IPI here. So basically, you can see for our method. Okay. You can see this kind of IPI for this MF also. Okay. But sometimes you mix the background here. You mix background here. Okay, we can also compare a little bit with data free turn. We can use L1 turn, also L2 turn. We can see that both turns are pretty good. Okay, are pretty good because it tolerates the noise. Okay, you can tolerate noise. And then for the CB10, okay, it's also very simple. Okay, very simple. Okay, because it's convex, right? You can use first method. You can do it. So and then the general is for two. Is two stage. Okay, it's two stage for color image. And then later we consider another approach. Okay, we add an extra stage. Okay, we propose 3-stage model to handle the color image. Okay, so basically it says that the stage 1 we do some you have some smoothing, right? And then we can do some lifting. Okay, basically because you have the, for example, for color image you have the RGB space, also many lab space, many other space, right? Basically all the space should be reasonable. Okay, we want to mix this kind of space. Okay, so then you can lift a little bit. From originally maybe you have RGB space, but you can also consider the LAB and then put it together. Okay, you get a higher dimension space, but with higher dimension you have better properties to eliminate the outlier. Okay, so what we do is that, okay, you do some smoothing, okay, in the first color space, and then we change it to another color space. We put it together, and then we do some thread holding. Okay, let me. So the idea looks very simple. Let me show you the details. Okay, so you have for example you have the D channels. Okay, for each channels you do the minimization separately. Okay, separately. Here we can slightly modify this kind of terms to integrate the missing values. Okay, missing values. And the data filter turn could be different, right? To L2 turn or also other turns to satisfy the other different noises. Okay, different noises. So and you have better mathematical properties because our model is very simple. Let me show you some numerical result. Okay, numerical result. Okay, so we call our method slide method smoothing, lifting, and thread holding. Okay, we compare with the FRC model and the PCMS model, or again the POS model. Okay, POS model. And so this is the image test. Okay, from the Berkeley set. Okay, Berkeley set. So this second image have some noise. Okay, so FRC is not good. PCMS is pretty good. Okay, but DPP is not so good. And for ours, you can see that we can get the contour. Okay, and then when you have some more information loss, okay, it's different difficulty contour, then you could fail. Okay, and for our case, we can still do it. Okay. And you can also have some blurring. In all cases, you can see we can get a very good result. Okay, so we can test more. Okay, so this again, this one you have some varying, okay, varying intensities. Okay, then for FRC, okay, you will get something like that. Okay, also for PCMS, DPP is not good. Okay, because this one is changing. Okay, it's have some trends to broken, okay, the color here. But for ours, you can see that in all cases, okay, we can get a very clear boundary. Also for color image, we can also do it, right? So this you have color, you want to segment it out, then so sometimes the other method could fail due to the different situation. But for our case, because we can always recover better smooth image, then we do the thread holding, you can get the result. More image. Okay, so this is noisy image, and we want to segment different parts. Okay, the red one, the red one, also the yellow one here. So you can see that for DBP, okay, it could be some mix here, and for our case, you can see that basically we can find the contour, find this contour. Also for this parameter image to send, okay, you can see that because the background is somewhat difficult to handle, but for us, because we have the lifting, okay, we have lifting, and then after the solution, we get some image like that. Okay, we can segment the result. More image, okay, but basically the same. We have tested many images. Basically, in all the cases, we can get better contours. Okay, so this is the same here, the same for the elephant image. And then another approach we want to present is a two-stage selective model, okay, for medical image. It is just the same as Professor Boykov. So what we need to do is that, okay, suppose you have some kind of image here, but suppose you are interested in some particular part, okay, for example. Then you use some maker points, okay, to put some maker points near the boundary, okay. Then you want to get some result. You can get this targetable region, okay. You want to get this one. So what we do is that we slightly modify our mesh model, okay. So still you use the H1 term, and then you use some penalty term, okay. You modify the weight here. You modify the weight here to the weight is generated, okay, from this kind of formula. You can integrate the information here. You have some points here, right? You integrate these points in as a weight, okay. So what we do is use this very simple one. You generate some distance constants, and you use H decomposition method to replace G, okay. So this is our model, okay. You can generate it. And then once you fix your weight here, okay, once you fix your weight here, then it's still H1 model, right? H1 model, then you can do very simple minimization, okay, okay. So you can prove some very simple or mathematical property, because our model is very simple, right? And you can do some numerical optimization, okay. Optimization, you can use the other method to do it. You can use okay. Basically, if you do adulating minimization, you can prove that the convergence rate, okay, is linearly convergence, okay, linearly convergence. Let me show you some covariant result. Okay, we compare with the active contour method, okay, or previous method. Let me show you. So this is the image. Okay, you have some maker points here, okay. And if you use the first method, sometimes you cannot get a perfect result. And the second method is also pretty good, but it depends on the initialization, okay. If you initialize with a small one, then you get the contour is pretty good. Basically, it's level set method, okay. Is active contour method. But if you slightly change it, it could be the contour like this one. But for us, the case is slightly different. So here again is the original image. What we get, the smoothing, okay, the solution smoothing image, okay, solution image like this one. And then you do the shear holding, you can get the contour here, okay, contour here, and you put it back. You can see that in this case we can get a very good boundary, very good boundary. Okay, so this is comparison. And for brain image, okay, in this sense, okay, you want to, for example, if you want to segment this out, you put some points along the boundary, okay, along the boundary, and then the previous method maybe does not, this one does not work, okay. But this is pretty good, but you lost a little bit here. But then for our case, you can see that this is the solution image, the smooth image, okay. Because you use a weight here, then all the part here will go, okay, will go. And what you remain is just this part, okay, information along this one. And then you do the shear holding, you get this contour, and you put it back, you get the target region. Okay. We have tested more results. For example, you want to segment this out, but it's rather difficult, okay, because this one is long convex. So we put some points here, so then you get a solution image, then you get this one, and then you get the region is here. And if you want to segment the right part, then you put some points here, so you get a solution image. After the shear holding, you get this image, then you get the contour here, more, okay, the same, okay. For example, if you want to, but now if you want to segment this part, then you get the solution image, and afterward you get this part, okay. So it depends. You can do it manually, okay. It's semi-supervised. The same, okay. Here, this one, basically the same. If you want to segment this out, we work on the 1 minus f here, okay. Then you do the smoothing. You do smoothing, you get this one, and then you should hold it. You can get a contour. Roughly the same. You can roughly determine the boundary here. Okay. So real quick. So okay. So basically, it's all okay. We propose the two-stage segmentation. It's based on the Mumford model. Okay. So what we do is you do some smoothing, and then you do some assured holding. Okay. For color image, okay, maybe you can do some. You have more information. Okay. You can compute the transfer the color space, and you put it together. You get some lifting. Okay. And then you do it separately. Then you do assured holding. You can get the result. It's pretty good. And for our model, okay, for first stage, okay, is convex. Is convex. You can get under my condition. You can get some unique solution. Okay, and then the model is very simple. Okay, you can it can be solved very easily. Okay, and fast. And usually there is no need to solve the model again if you want to slightly modify the threshold or lambda of phase change. Okay. And you can easily extend this one to general case, okay, to blurry image, non-Gaussian noise or information loss, okay. And we are working on this one for the manifold segmentation, and I did not present. Maybe I can present next time. So in fact, for the if you want to segment the image from the manifold, okay, surface, you can still do it, okay. It also works, okay. And we also link this image segmentation task to image restoration. Basically, for our first stage is image recovery model, okay, H1 model, and we can by combining all these things, we can get an efficient algorithm for color image and medical image segmentation. In case you are interested, we at least some reference here. The first one is for the medical image, and this one is for the color image for select algorithm, and then this one is for color image, and the previous two are for the gray image. Okay, gray image. Okay, thank you.
Other questions?
Yes.
So for the color images, when you do the denoising, is there a correlation between channels considered, or just individual channel by channel?
We do it channel by channel because by this you can but sure you can use vector to your level to do it. But for us, we chose to do this channel by channel because you can do some parallelism. Do it, okay. This is basically the same. Okay. The same. So currently we do is channel by channel, then you do some transform and you mix it together, and you get the higher dimension space. It's just like the same idea of kernel trick. Okay, you lift the dimension. Okay, then you get better result. Yes.
So the stage 2, I wasn't clear about the threshold. Is it like a Prof dependent threshold choice?
In fact, because we have a smoothing part, okay, for the first stage you do some smoothing, and when you do some smoothing, and if you look at the histogram, so it's very smooth, okay, it's a very simple shape. Then what we do is use k-means method. Okay, if you want to determine it automatically, then you define the k. Okay, you give you k, you use k-means to find the high peak or whatever. You do some clustering, then you find the center.
You should go back one of the examples. I think if you choose a different threshold, like anyway.
You can choose, but it depends on your need. If you can use k-means, it's pretty good. It's already good.
Looks one example.
The previous one. But originally, in fact, we mentioned this one is going. This kind of parameter for this m with k-mean, basically, if you look at the histogram of this smoothing image, you have it's like this. Then you do some two clustering, then you can find. For example, if you look at the histogram, you will get two parts like this one. Okay, two parts. So you do some cluster. Okay. Now because shape is very simple, so you have two parts here. So you will find a center here, and you find another center. And then if you want to separate it, you just use the middle value. Then you do it automatically. Yeah.
So if we change the threshold a little bit, the segmentation will change also.
We slightly change. Yes, you will change, but it's rather stable. For example, what we change is here. This is rule m and this rule 1 are different, right? Are different parameters, but you can see that the result are somewhat stable, but it's still sensitive. But it depends. Yeah, it depends.
It's almost like you need another segmentation to do this.
You can see that. You can see that. But basically, the idea is that in the first stage, you have some smoothing. You can eliminate some tiny structures there. Then for the second step, it's very simple. Okay, you don't need a very complex method. Yeah. But you can do as other method. You can give the parameters. Then you can segment it. But what we can do is we can automatically do it. Okay, we just use k-mean. You can automatically determine the parameters. Yeah.
Okay, thank you again. So we're going to stay here for 15 minutes until the copy.